Welcome to this walkthrough of LeetCode problem number 1417, reformat the string.
In this problem, we'll explore how to transform a given string so that no two adjacent characters belong to the same type, letters or digits.
Let's dive into the details and solve it step by step.
This problem requires us to reformat a given string so that no two adjacent characters are of the same type.
The input string, S, contains only lowercase English letters and digits. Our task is to rearrange the characters so that letters and digits alternate. If this is not possible, we should return an empty string.
For the output, we need to ensure that no two neighboring characters are both letters or both digits.
Let's explore some examples to clarify the requirements further. In the first example, the input string is S equals A0B1C2. This string contains three letters A, B, and C and three digits 0, 1, and 2. Since the number of letters and digits is equal, we can alternate between them. One valid arrangement is 0A1B2C, another is A0B1C2. Any order that alternates letters and digits is considered valid.
This demonstrates that reformatting is possible when the counts of letters and digits are balanced.
In the next example, the input string is S equals LeetCode.
This string consists only of letters, with no digits at all. Since there are no digits to alternate with, it is impossible to create a valid reformatting.
As a result, the output is an empty string. This highlights that if one type of character is completely missing, reformatting cannot be achieved. Now, consider the example where S equals 122985739.
Here, the string contains only digits and no letters.
Similar to the previous example, there is no way to alternate between letters and digits because letters are completely absent.
Therefore, the output is again an empty string. This reinforces the idea that having only one type of character makes reformatting impossible. Finally, let's look at the input S equals COVID 2019. This string contains 6 letters C, O, V, I, D and 4 digits 2, 0, 1, 9. Since there are more letters than digits, the reformatting starts with a letter and alternates with digits.
One valid output is C200V1I9D. The constraints specify that if one type has more characters, the reformatting must begin with that type.
Additionally, multiple valid outputs are possible as long as the alternation rule is followed.
With this understanding, let's summarize the constraints and edge cases for this problem.
The string length can range from 1 to 500, and it will always contain only lowercase letters and digits.
If the count difference between letters and digits exceeds 1, or if only one type of character is present, reformatting is impossible.
Otherwise, alternating sequences must follow the rules described. To solve the problem of reformatting the string so that no two adjacent characters are of the same type, we explored multiple approaches. First, we considered a brute force method that involves generating all possible permutations of the string and checking each one for validity. This approach uses recursive backtracking to generate permutations and validates whether no two adjacent characters are of the same type. However, while this method is conceptually straightforward, it is extremely inefficient for larger strings due to the factorial growth and the number of permutations. The time complexity is O(n) for generating permutations, and each validation step takes O(n). Additionally, the recursive nature of the algorithm adds to the space complexity. Ultimately, this approach is impractical for real-world use, especially for large inputs, but it provides a baseline for understanding the problem space. A more efficient strategy is the greedy approach, which simplifies the problem by separating the characters into two groups, letters and digits.
Once separated, we check if reformatting is even possible by ensuring that the absolute difference between the sizes of the two groups is no greater than 1. If this condition is met, we construct the result by alternating characters from the larger group first.
This ensures that the output string adheres to the rule that no two adjacent characters are of the same type. This method achieves linear time complexity, O(n), as it involves a single pass to separate the characters and another to reconstruct the string. The space complexity is also O(n), to store the separated characters. While this approach uses additional space for the intermediate lists, it is highly efficient, handles all edge cases, and is easy to implement, making it an optimal solution for this problem.
Another possible solution is the two-pointer approach, which avoids explicitly separating the characters into lists. Instead, we traverse the string once to count the number of letters and digits. Then, using two pointers, one for letters and one for digits, we alternate between the two types of characters as we construct the result string. After adding a character, the corresponding pointer is adjusted. This method saves space compared to the greedy approach since it doesn't require intermediate lists, making its space complexity O(1), aside from the output string, which isn't counted. The time complexity remains O(n) for traversal and construction. However, this approach can be slightly harder to implement and debug due to the need for careful pointer management. While it is a valid alternative, the savings in space are minimal, and the increased complexity in implementation may not justify its use over the greedy method. The greedy approach was chosen as the optimal solution for this problem. By separating the string into letters and digits, we simplify the task of ensuring no two adjacent characters are of the same type. Alternating characters from the larger group first guarantees a valid result while maintaining efficiency. This method is preferred because it is both simple to implement and easy to debug. With a time complexity of O(n) and a space complexity of O(n), it is highly performant and handles edge cases, such as unequal group sizes, naturally by checking the size difference at the start. While the two-pointer approach is slightly more space efficient, the greedy method is easier to understand and implement without any significant trade-offs in performance. The brute force approach, though valid, is computationally infeasible for all but the smallest inputs. A key insight here is that letters and digits can always alternate if their size difference is at most 1, which reduces the problem to a straightforward process of grouping and reconstruction. By prioritizing the larger group, we eliminate unnecessary checks and ensure validity. Finally, let's summarize the complexity of the chosen solution. The time complexity is O(n), stemming from the single-pass separation of letters and digits and the subsequent reconstruction of the result string. The space complexity is O(n), due to the storage of the separated groups. This balance of simplicity, clarity, and efficiency is what makes the greedy approach the best fit for this problem. It avoids unnecessary overhead, handles edge cases seamlessly, and provides a clear path to implementation. Overall, this strategy ensures that we achieve the desired reformatting in an optimal and reliable manner. In this problem, we are tasked with reformatting a string such that no two adjacent characters are of the same type, meaning no two letters or digits can appear next to each other. If this arrangement is not possible, we return an empty string. To solve this, we'll use a greedy algorithm. The first step is to divide the string into two groups, letters and digits. By traversing the string, we can build two separate lists, one for alphabetic characters and one for numeric characters. This separation allows us to work with the two groups independently, simplifying the process of interleaving them later. Once we've separated the characters into letters and digits, the next step is to check if it's possible to reformat the string. For the interleaving to work, the absolute difference between the counts of letters and digits must be at most 1. If the difference exceeds 1, we know it's impossible to alternate between the two groups without having consecutive characters of the same type, so we return an empty string immediately. If it is feasible, we proceed to interleave the characters. Here, the group with more elements will start the reformatted string, ensuring we don't run out of characters during the process. Using a greedy approach, we alternate between adding one character from each group until all characters are used. Finally, we combine these interleaved characters into a single string and return the result. There are a few key insights that make this approach effective. First, separating the characters into letters and digits simplifies the logic, as we can treat each group independently. The feasibility check, which ensures that the absolute difference between their counts is at most 1, prevents us from attempting to solve an unsolvable case. Another important consideration is deciding which group starts the interleaving process. By always beginning with the larger group, we ensure that we don't run out of characters prematurely. In terms of data structures, we use lists to store the letters and digits separately because lists allow efficient appending and straightforward iteration. Finally, the resulting string is constructed efficiently by joining the interleaved characters. Let's analyze the complexity of this algorithm. The time complexity is O(n), where n is the length of the input string. This accounts for the O(n) time required to traverse the string and separate the characters, as well as the O(n) time needed to interleave them. The space complexity is also O(n),
as we create two separate lists to store letters and digits.
Now, considering edge cases, if the input string is empty, the result is an empty string.
Similarly, if the string contains only letters or only digits, interleaving is impossible, so we return an empty string. Lastly, if the counts of letters and digits differ by more than 1, the result is again an empty string. However, when the counts are equal, the interleaving alternates perfectly, creating a valid result.
Let's walk through an example. Consider the input string s equals A0B1C2.
First, we separate the characters into two groups, letters equals A, B, C, and digits equals 0, 1, 2. Next, we check the feasibility of interleaving. The counts of letters and digits are both 3, so the absolute difference is 0, which is valid. Since either group could start, we decide to begin with a letter. During the interleaving process, we alternate between the two groups, adding A, then 0, then B, then 1, and so on. This sequence continues until all characters are used. Now, let's look at another example with the input string s equals ABC1234. After separating the characters, we have letters equals A, B, C, and digits equals 1, 2, 3, 4. Checking feasibility, the counts are 3 and 4, yielding an absolute difference of 1, which is valid.
Since the digits group is larger, we start with a digit. The interleaving proceeds as follows: add 1, then A, then 2, then B, and so on. Finally, after using all characters, we append the remaining digit 4. In both examples, we successfully reformatted the strings to ensure no two adjacent characters are of the same type. The first example produced the result A0B1C2, while the second produced 1A2B3C4. This algorithm guarantees a valid reformatting if the input string meets the feasibility condition. Otherwise, it returns an empty string. By following these steps, we achieve an efficient and reliable solution to the problem. Here, we start by defining the reformat method within the solution class. The goal of this method is to rearrange the given string so that letters and digits alternate as much as possible. To achieve this, we first separate the input string s into two distinct lists, one for digits and one for letters. We iterate through each character in the string, checking if it's a digit using the isDigit method. If it is, we append it to the digits list, otherwise, it goes into the letters list. Next, we check if the absolute difference between the lengths of these two lists is greater than 1. This is because if the difference exceeds 1, it means that alternating the characters is impossible, so we return an empty string immediately. After this, we ensure that the larger group, whether it's digits or letters, is the one we start with. This is done by comparing the lengths of the two lists and assigning the larger and smaller variables accordingly. Finally, we initialize an empty list called result, which will store the interleaved characters as we process both groups. The interleaving process begins by iterating through the indices of the smaller list. For each index, we add one character from the larger list and one from the smaller list to the result list. This ensures that the characters alternate as much as possible. After completing the loop, there may be one character left in the larger group if its size exceeds the smaller group by 1. In that case, we append this remaining character to the result. Finally, we join all the characters in the result list into a single string using join, and return it. This gives us the reformatted string with alternating letters and digits, or an empty string if it wasn't possible to create such an arrangement. Here, we start by importing the necessary utilities and defining our solution class along with the reformat method. The goal of this method is to rearrange the input string such that digits and letters alternate while maintaining their original order within their respective groups. First, we initialize two lists, digits and letters, to separate the numeric and alphabetic characters. Then, we iterate through the input string using a for each loop. By checking if each character is a digit using character.isDigit, we can add digits to the digits list and all other characters, assumed to be letters, to the letters list. Next, we handle the edge case where the difference in size between these two lists exceeds 1. If that happens, it's impossible to interleave them properly, so we immediately return an empty string. Finally, we identify which group is larger. If the digits list is bigger, it gets assigned to larger, and letters become smaller. Otherwise, the roles are reversed. This ensures that the larger group always starts the interleaving process.
To construct the result, we use a string builder and interleave characters from the larger and smaller groups. With a for loop, we append one character from each group at a time. This alternation continues until we exhaust all characters in the smaller group. After that, if the larger group has one remaining character, we append it to the end of the result. This handles cases where the sizes of the two groups differ by exactly 1. Finally, we convert the string builder back to a string and return it. This ensures the output meets the problem's requirements by alternating characters from both groups while handling edge cases gracefully. The solution is efficient and ensures the string is reformatted correctly or returns an empty string when it's impossible to do so. To solve this problem, we start by separating the letters and digits from the input string. For the input s equals A0 B1 C2, we initialize two lists, digits to store all numerical characters and letters to store all alphabetic characters. We then iterate over each character in the string. When we encounter a, we recognize it as a letter and add it to the letters list, making it a. Next, 0 is identified as a digit and added to digits, resulting in 0. This process continues for the remaining characters. B and C are added to letters, and 1 and 2 are added to digits. By the end, we have letters equals a, B, C, and digits equals 0, 1, 2. After separating the two groups, we check the difference in their sizes. Since both groups have 3 elements, the absolute difference is 0, which means it's a valid configuration for reformatting. With both groups being equal in size, we assign letters as the larger group and digits as the smaller group, ensuring compatibility for interleaving later on. Now that we have separated the groups and determined their sizes, the next step is to interleave characters from the larger and smaller groups. We initialize an empty list called result to store the interleaved characters. Starting from index 0, we append characters alternately from letters and digits. First, we add letters, 0, which is at end digits, 0, which is 0, resulting in result equals a 0. Next, we append letters, 1, and digits, 1, making the list a 0, B, 1. Finally, we include the last pair, letters, 2, and digits, 2, updating the result to a 0, B, 1, C, 2. Once we finish interleaving all elements, we convert the result list to a string, which gives us the output A0 B1 C2. This is the reformatted string that alternates between letters and digits. For the second example, the input string is s equals 123 ABC. Just like before, we start by separating the characters into digits and letters. The digits are 1, 2, 3, and the letters are a, B, C. Since the size of both groups is 3, the absolute difference is 0, indicating that the configuration is valid. Here, since the sizes are equal, we can arbitrarily decide which group to treat as larger. For this example, we assign digits as the larger group and letters as the smaller group. With this setup, we can now proceed to interleave the characters from both groups. To create the reformatted string, we again initialize an empty list called result. Starting with the first character of each group, we append alternately from digits and letters. Adding digits, 0, which is 1, and letters, 0, which is a results in 1, a. Next, we append digits, 1, and letters, 1, updating the list to 1, a, 2, b. Finally, we include the last pair, digits, 2, and letters, 2, giving us 1, a, 2, b, 3, c. After interleaving all the characters, we convert the result list to a string, resulting in 1a2b3c. This is the output for this example. Now, let's consider a new scenario where the sizes of the groups differ by 1. In the third example, the input string is s equals ABCD123. After separating the characters, we have letters equals a, B, C, D, and digits equals 1, 2, 3. Here, the size of the letters group is 4, while the size of digits is 3. The absolute difference between the sizes is 1, which is still valid for reformatting. Since letters is the larger group, we designate it as larger and digits as smaller. To interleave the characters, we initialize result equals and append alternately from the two groups. First, we add letters, 0, and digits, 0, resulting in a 1. Then, we append letters, 1, and digits, 1, updating the list to a 1, B, 2.
Next, we include letters, 2, and digits, 2, making the list a 1, b, 2, c, 3. Since the letters group has one extra character, we append it to the end, resulting in a 1, b, 2, c, 3, d. Finally, we convert the result list to the string a1, b2, c3, d, which is the output for this example. This demonstrates how we handle cases where the groups differ in size by 1. To analyze the time complexity of our solution, we start by looking at the step where we separate the digits and letters. Here, we use a single for loop to iterate through each character in the input string. For each character, we perform an O1 operation to determine if it's a digit or letter. Since this loop processes all n characters, this step takes O(n) time. Next, we calculate the lengths of the digits and letters lists and compare their difference. This computation involves basic length checks and a comparison, all of which are O1 operations. Following that, we reorder the characters. This involves determining which list is larger, which is O1, and then interleaving characters from the two lists. The interleaving loop runs for the smaller of the two list lengths, which in the worst case is O(n)/2, simplifying to O(n). Finally, appending any remaining character from the larger list, if necessary, is an O1 operation. These steps together give us the time complexity for reordering as O(n). The final step in our time complexity analysis is joining the result list into a single string. The join operation iterates through the result list, which contains all n characters of the input string, making this step O(n). When we combine all the steps, we have O(n) for separating characters, O1 for length checking, O(n) for reordering, and O(n) for joining the result. Summing these together, the dominant term is O(n), so the total time complexity of the solution is O(n). Now, for space complexity, we start by considering the space used by the digits and letters lists. These lists store characters from the input string, and in the worst case, one list could hold all n characters while the other is empty. Together, they use O(n) space. Next, we analyze the space used by the result list. This list holds the interleaved characters and will ultimately contain all n characters from the input string, making its space usage O(n). Additionally, there are a few variables like larger and smaller used as references or for intermediate computations. These variables require only O1 space since they do not grow with the size of the input. Combining these components, the total space complexity is O(n) for the digits and letters lists, O(n) for the result list, and O1 for additional variables. Thus, the overall space complexity of the solution is O(n). When comparing this solution to a brute force approach, the efficiency becomes even more apparent. A naive method might involve generating all possible permutations of the input string and checking each one to see if it satisfies the conditions. This would result in a factorial time complexity of O(n), as there are n permutations of the string. In contrast, our solution achieves a time complexity of O(n), which is dramatically more efficient. Similarly, the brute force approach would require storing all permutations, consuming O(n) space in the worst case. Here, our solution uses only O(n) space, making it far more scalable. Whether the input string has an equal number of digits and letters or the difference between their counts exceeds 1, the time complexity remains O(n), because we process all n characters. The space complexity is also consistently O(n), since the storage requirements depend only on the size of the input. This consistency makes the solution robust and efficient for all cases. One common mistake when solving this problem is not handling cases where the counts of letters and digits differ by more than 1. If the difference exceeds 1, it becomes impossible to alternate letters and digits in the output. This is why it's important to validate the input constraints before proceeding with any logic. Another mistake is incorrect index management during the merging process. If you don't properly alternate indices while combining letters and digits, you could end up with 2 consecutive letters or digits, which violates the problem's requirements. Lastly, skipping edge cases can lead to runtime errors. For example, an empty string or a string that contains only letters or only digits must be handled explicitly. Always account for these possibilities to ensure your solution is robust and doesn't break under unexpected inputs. Now, another mistake we often see is using inefficient operations like sorting the string or repeatedly concatenating strings.
Sorting can add unnecessary computational overhead, especially since it has a time complexity of O(n) log n. Similarly, using operations like repeated string concatenation is inefficient in Python because each concatenation takes O(n) time. Instead, aim for list-based operations, which are much more efficient.
Additionally, it's crucial to maintain the correct output format.
When the counts of letters and digits differ, the output must start with the type that has more characters.
Failing to adjust your starting character based on counts can lead to an invalid output.
Always check these counts up front and design your solution accordingly.
This problem is a favorite in interviews because it tests several important skills. First, it highlights your ability to manage multiple pointers and alternate between different groups of characters.
It also assesses how well you handle edge cases and constraints, which are critical for writing reliable code.
Efficiency is another key aspect here.
While a brute force approach might technically work, interviewers are often looking for O(n) solutions that rely on linear scans and efficient string construction. Beyond the implementation, interviewers will pay attention to how you communicate your thought process, such as explaining how you determine the starting character and how you handle edge cases. Additionally, you should be prepared for follow-up questions or variations, like handling additional character types such as symbols or reformatting strings based on different rules. This demonstrates your ability to adapt to new challenges. If you're looking for related problems to practice, there are several great options on LeetCode. For example, Problem 937, Reorder Data in Log Files, focuses on sorting and rearranging strings based on multiple criteria. Problem 791, Custom Sort String, requires you to reorder characters in a string based on a custom priority, which is a good exercise for understanding sorting with constraints. Another highly relevant problem is 767, Reorganize String, where you're tasked with rearranging characters so that no two adjacent characters are the same.
Lastly, Problem 451, Sort Characters by Frequency, challenges you to group and rearrange characters based on how frequently they appear.
These problems share conceptual similarities and can help you strengthen your skills in string manipulation and pattern recognition. When it comes to alternative approaches, one simple and efficient method is to split the string into two separate lists, one for letters and one for digits. These can then be interleaved based on their counts, achieving a time complexity of O(n).
However, this approach requires extra space for the lists. A more space-efficient option is to use in-place rearrangement with two pointers, swapping elements directly within the string.
While this saves space, it can be more challenging to implement and debug.
Another option is to use a greedy algorithm, dynamically choosing the next character, letter or digit based on availability and constraints.
This method is highly flexible and can handle variations of the problem, but it might be overkill for simpler versions.
Each approach has its trade-offs, so choose the one that best suits the problem's requirements and constraints. Great job reaching the end.
In summary, we tackled the problem by splitting the string into letters and digits, and then interleaving them to meet the requirements. This problem highlights string manipulation skills and careful handling of edge cases. Thanks for following along, and don't forget to like, share, and subscribe for more content like this.
See you in the next one. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!